Hello, good morning everybody. I'm the resident data science expert for this webinar and one of the data science guys here at RapidMiner. Let's get started this morning. I just have RapidMiner Studio open here, so if you were to open Studio with me, this is the view that we'd see, or if you were to download Studio and open it for the first time, you get the same view that we're looking at here. Just to give you an idea, it's a visual programming platform, so by that I mean code optional. A lot of what we're going to do today is just going to be dragging and dropping some operators into the canvas, building out a visual workflow, and showing off some predictive maintenance inside of RapidMiner. So what I'll quickly do is I'll grab some data and then kind of talk about it in the realm of predictive maintenance and some of the examples that were talked about by Leslie. So quickly, I'm just going to grab this machine sensor reference data here. Anything that I grab from this repository window is either pieces of data that I've stored or models that I've stored that I want to use or deploy, or they're simply workflows that I've already built and want to embed into another process. Most of what I'm going to do from here on out is actually be pulling operators from my Operators tab or pre-built building blocks that I've built specifically for using predictive maintenance inside of RapidMiner. So what we'll do is we'll go ahead and run this data very quickly. If I hit run here, it should bring me to my results tab. I did have everything hooked up. You'll see I'm working with just an array of sensor data. I think I've got sensors 1 through 25 here to the end. I've got a machine ID, so I know what machine's being pulled off here. And I've got whether or not this has failed. So this is my historical data. This is stuff coming off the floor on machines that have failed, and I'm kind of being tasked with generating a model that'll allow me to do predictive maintenance in RapidMiner. So this way I can say, okay, these sensors are showing characteristics of a failure. Let's make a maintenance decision here to keep this machine up and running, and then ultimately these decisions result in cost savings for the business. This is pretty analogous to a lot of the previous use cases that Leslie so wonderfully brought up before. So without further ado, I'll kind of jump in and show you how we go from this piece of historical data and piece of reference data and actually build out a model so that way we can deploy that model and actually do predictive maintenance inside of RapidMiner. So set out with the goal of let's start with our data. Let's identify some key attributes that are the biggest cause of issue, and then from there push it through some sort of machine learning so that way we get a prediction out, validate that prediction, and deploy that prediction all within a single platform. So what I'll do is I'll jump. I do have a statistics view here, so I can take a data discovery dive. I can take a look. I've got I've already named my sensors. I've got a small amount of examples, but again, this is an in-memory solution, so I want to be able to run this and get meaningful results as quickly as possible for the demonstration. And I already have 2 special attributes, so my machine ID is already getting handled as an ID for RapidMiner. So if we were ever to push this through machine learning, we wouldn't get rules like, if machine ID is M_001, predict fail or predict non-failure. So ID works in that RapidMiner keeps that attribute, but doesn't actually use it in any of its algorithms. Same thing happens with label. The reason why failure is green is because we're telling RapidMiner this is the attribute we want to predict. So we already know off the bat RapidMiner knows what to do with our ID, and it knows what to do with our label or target variable, if you will. So if we jump into statistics here, I can take a look. I've got different data types, so most of my sensor data is numerical, which looks great. I don't have any missing variables, so there's no, this is a very well-structured data set, but these are all problems that I can identify here and handle if I need to in some meaningful way. And then also I do get some statistics, so I can see, I can get a relative snapshot of what sensor 1 is doing, and maybe I have some background into what type of machine this is and where the sensor is, so I can see, right off the bat, do I have some dangerous values? I can open up my chart here. I can say, this is my average distribution. Everything out here might be a little warning or telltale sign, so I can already check and look at my sensor data and see, is there anything that right off the bat I can say might be a little dangerous? A lot of this data visualization is just primarily data discovery, so I can switch between chart types here. And I can take a deeper dive into my data. I can plot multiple aspects. Maybe I've got time-dependent data or temperature-dependent data, and so I'd be able to track those. I'd be able to take a data discovery dive into those and actually track, what's happening on temperature, what's happening on my sensors when I track for specific temperature types or specific pressure data. I have the availability to look at that in my platform. So the fact is I'm working with very generic data, so what I can do is I can jump back into design. I know I don't have anything in terms of data prep where it's like missing values or anything like that, but the step 2 is, or step 1 has been load in the data and take a look at it, take a dive into our data and discover it. The next step would be to say, okay, let me try to identify key sensors that would probably be the dominant predictors of any sort of maintenance on my machines. So what I actually have here, and I'll actually walk us through, is I have a building block that's useful. So this is a set of operators I've already built in RapidMiner for this purpose. And the reason why I'm inserting it here is because the rest of my demonstration will be fairly straightforward, and I'll only need to drag and drop a few operators. This step would probably take me upwards to about an hour to drag and drop and configure and talk about each operator. So what I've done is I've gone ahead and built this building block. So I'll go ahead and grab determine influence factors. So it is a block of operators, so I'm going to drag this onto my workflow here. It is a sub-process, so I can come inside of this. So once I've brought inside, you'll see, I've got an array of operators going on here, all of which I've managed to drag from my operators tab and drag onto the canvas and configure. But what I'm going to do is I'm going to add a couple of breakpoints here, and I'll walk through what's going on in this data set to kind of get an idea of some of the things that you can be doing with your predictive maintenance data inside of RapidMiner. What I'll talk about here is I'm individually weighting all of my attributes via multiple different weighting methods, and then generating an attribute based off of that weight. I'll then append all of these together right here. So what I'll do is I'll go ahead and run this so you can get an idea of what this looks like. So once I've grabbed this, I've got individual weights for each sensor and the type of weight method that's there. So if I sort on attribute here, you'll see I'll get, for sensor 1, I should have 4 different weights. All of my weights are located here, and I've got a correlation, a Gini index, information gain, and an information gain ratio. So I've got 4 different weights generated here. They've all been appended together, so I've got all of my data. The next step, I'm just going to quickly pivot that data to get a good idea of, condense down my data set. I've generated each of the weights as their own attribute, and the next step is to actually pivot around this data. So what I do is I just take the sum of the different I sum over the different methods. So if I continue running this, we should get an aggregation where I get a new variable, here it is, of importance. So it takes the total contributions of all the different weights, and so I can sort based off of importance here. So I've identified that sensor 7 is the sensors 7, 6, 8, and 5 tend to be the sensors of most importance to my machines when it comes to predictive maintenance. So I have a good idea of what sensors are useful, and I can go down the list and see what sensors are not so useful to me. So from there, what I do is I just normalize that data, and ultimately I just sort it so I can get an importance here, and then after the normalize, see my sensor 7 is at an importance of 1, and sensor 24, which had the lowest amount of weight importance, is now my 0 range. So from there, I can get a final list of ordered attributes, so I know that sensor 7 is of most importance to me, and I can see how that drops off via each sensor. So here I've just taken a look and trying to find out, what areas of my machine are most important to our predictive maintenance case. So what I'm going to do is I'm going to remove those breakpoints because it's great to see what sensors are providing useful information to those predictions, but now I actually have to make a prediction. So step 3, what I'm going to do is I'm just going to quickly add a multiply from the operators window here, and all this is going to do is allow me to send this data set out to multiple things. So it just copies my data set here. Each output port is a new copy of that data set. So what I can quickly do is I can say, okay, generate a KNN. So I'll use a KNN here just for simplicity use. But if I take a look in here, inside of my predictive folder, so these would be anything that I want to do any sort of predictive analytics around. I do have KNN, naive Bayes. There's a whole slew of decision trees in here, including random forests, as well as the H2O gradient boosted decision trees. I can take a look. I've got plenty of neural nets, including the H2O deep learning. Both of those H2O operators have been a brand new addition to our library. I've got plenty of regression analysis, both linear, logistic, and a couple other regression options, as well as support vector machines, a vast array of those. And then recently there was an article saying that ensemble models are the hottest used models for data scientists. So there's an extensive ensemble models folder, which again will allow you to utilize all of the other machine learning algorithms we have available in RapidMiner. So you can see you have an extensive library of tools here for machine learning and the availability to actually make these predictions as good as possible. So with that, I'm just going to run with the simple model of a KNN, and I can easily just go ahead and hook this up and generate a model based off of like a K of 5 or something like that. So I can go ahead and run this. All this tells me is I've generated a model based off of a nearest neighbor, and it classifies yes or no. So it just tells me what the model's doing. I have no idea if this model is great or not. So the next step would be let's validate this model. So I'll go ahead and copy out my KNN, and I'm going to grab a cross-validation for this case. I'm going to output a couple of things. I think I really only have to take my performance vectors. So if I come inside my validation, I can quickly say, okay, grab me that KNN that we had. Ultimately, I can grab training. I can grab my model. So on the left-hand side, inside of my cross-validation, I'm parsing up my data set into training and testing chunks. The cross-validation will allow me to utilize 100% of my data for training and testing, which is fantastic. So what I can do is I'll keep my K of 5. I'll say I need an apply a model. What I'm going to do here is I'm just going to grab from my RapidMiner Wisdom of Crowds. It's an opt-in tool for RapidMiner users. We track what operators you're placing onto the canvas and what operators you are connecting those operators to. And sometimes we track specific parameters. In this case, apply model is down here saying 99 or 100% of users use an apply model and they have a KNN inside of a cross-validation. So I was able to click and drag that operator instead of searching for it. Same thing with the performance operator. So really good tool for getting up and started for a new user, as well as I myself as an experienced user, I find myself using the Wisdom of Crowds often because it's just what I need is always down there, so I'm clicking and dragging it. As easy as that. So all these operators do is apply this KNN to my testing data, so that way I can actually get a confusion matrix out and see how my model is actually performing under this machine learning with this data set. So I can go ahead and run this. It is a KNN, so I get about a 64.67% accuracy. I have no idea if if my K selection is proper, there is a bit of a swing on there, so I possibly could be doing up to 75%. But I could also, on the flip side, also only be doing around just better than a coin flip. So the next step I could easily say is, okay, I don't know what the best option for a KNN is, and I'll have RapidMiner optimize this for me. So I can easily drop in and optimize parameters and say, okay, validate this model for me based off of performance. So what it'll do is I'll say, okay, give me a K. Let's start that K at 1. We'll go to a K of 50, and we'll do that in 50 steps. So RapidMiner will actually pick the best possible K for me, so I don't have to guess and check. And this is really handy when you're ultimately trying to automate this entire process. So as you're getting new sensor data, maybe you get updates weekly and want to retrain a model off of the new sensor data that week or that month. You'd have the availability to know that that process is always automated, and that automation encompasses the optimization of your models. So if I send this out, I can go ahead and run this. I should see a jump to about a 70% accuracy, which is a lot better than what I was doing. So 70% of the time, I'm making the correct prediction on whether or not this machine should get maintenance, which is great, or whether or not this machine is showing the characteristics of a machine that should be maintenance. So I'd at least be 70% of the time that this machine is showing the similar sensor characteristics that a machine that has broken down in the past had been showing when it broke down. And I can easily log this information as well. But what I'm going to do here is, now that I've shown you how to actually go about building out this optimization, the next step is, if I'm satisfied with this model, is I could easily do something like I want to build this model and deploy it in the same process. I already have a set of data that I want to deploy over, which is my machine sensor data. So I could easily grab and apply model here, and I can send out my KNN that I've just generated, and I can send out my machine sensor data. And then lastly, I think I need a sort. So I can send in my example set here, and I can go, based off of a specific attribute name, I want to sort off of confidence yes. We'll do increasing, and then lastly, I want a remove columns, because I only want my scored data. So what I'll do is I'll say select attributes, all, and then I'll do invert selection. So what this will do is it'll only keep any of my prediction attributes for me. So I can go ahead and run this. I've now deployed that model we just generated, so I can see I've got plenty of machines 137 through 272. And then now I've got a prediction, and they're sorted based off of the confidence of that prediction. So I can see I've got a ton of machines here that have been predicted no, and I've got a handful of machines that have predicted yes. They're showing characteristics of machines that should get maintenance. So this kind of small, deliberate process is really useful. So really analogous to all types of predictive maintenance use cases inside of RapidMiner. Hopefully it shows off how quickly I can go from loading in a data set, doing some sort of discovery, especially if I've done this kind of discovery before. I can be utilizing sets of operators that I use for identifying key attributes all the time, as I did with those building blocks. Next, I can automate my model generation and model deployment inside of a single process. So maybe every couple of months I want to retrain a model and deploy it over the floor. I could easily do that, or I could easily store this model and deploy this model weekly, so I can track, or weekly or daily or hourly or what have you, based off of the sensor information coming in from the machine. And I'd have the availability of scheduling those processes to run if I'm utilizing RapidMiner server. Lastly, what I'll do is I'll actually open up a full processed version of this data. I don't actually want to save this because I have everything here. I've got that influence factor that I've generated. What I can also do is I can create a log so I can track the different types of KNN, and I can save that data set so I can see model performance based off of the automated KNN. That's what's going on here, and this is processing those scores in a very similar way that I did. Again, ultimately, I'm pulling in model equipment failure data based off of observations of past machines that I want to generate a model upon and apply that model to current machines in order to anticipate machine failures. I load through the data. I define influence factors. I then train a model and automate that model generation process, and then finally I deploy that model either on my machine floor or in my manufacturing center or what have you. And then ultimately the outputs, I get a set of influence factors for that model. I get a KNN optimization log and failure predictions for my current machines. So if I go ahead and run this, you'll notice I get the same set of results. My log tells me if I sort on accuracy here that I had a K of 37, so I can get all of this information out on any models that I'm optimizing as well, whether it's a decision tree or a neural net or a support vector machine. I can always track what's getting optimized and why and how well those optimizations are performing.